warm welcome to the class of electrochemistry. In the last lecture, we have talked about the molar conductance and its variation as a function of concentration for strong electrolyte, and the variation follows a trend like this. You see that there is a linear variation, and if you reduce the concentration of the solution, then its value increases, and ultimately, I mean, if you extrapolate this to concentration 0, then you will end up in getting a quantity which is called the limiting molar conductance or molar conductance at infinite dilution. I have explained to you what is meant by infinitely dilute solution in connection with conductance. I repeat that infinitely dilution means that if you further dilute the solution, that does not bring in any change of the conductance of the solution. That means all the ions are free to move, there is no probably there is no interionic attraction, and that is why it reaches some limiting value. So, this is for a typical strong electrolyte. Strong electrolyte which is assumed to be dissociated to the fullest extent all the time when you dissolve this strong electrolyte in water. But if it is a weak electrolyte like acetic acid, so it dissociates as CH3COO minus plus H plus in aqueous medium, and what happens that if it is a moderately concentrated solution, then this is not fully ionized. If a fraction of the of this left hand side is ionized to get you this proton and the acetate ion. So, therefore, if you keep on diluting this acetic acid solution, then the extent of this dissociation increases. Now, as I have explained to you, like lambda m is equal to kappa times the volume. So, if you dilute the solution, then although kappa is also reducing, that is specific conductance is also reducing, but the value of this volume is much I mean increase of volume is much higher compared to the decrease of this kappa, and as a result of which what happens, this lambda m increases. But on top of this, an additional thing comes into picture is this extent of dissociation or the degree of dissociation. So, when you dilute, in addition to the increase of volume, and there is an additional term which superimposes onto this effect of increase of volume is the extent of dissociation. So, extent of dissociation increases. So, therefore, that is why, so it keeps on increasing, but this increase of this lambda m as a function of concentration, when this concentration is reduced, that is as a function of dilution, that it does not follow a linear trend, but a non-linear curve like this is followed. So, therefore, direct extrapolation of this lambda versus square root of c, this expression is not good enough to find out the lambda m 0, that is the limiting molar conductance value for weak electrolyte. Incidentally, you can express this lambda m for strong electrolyte like this: lambda m is equal to lambda m 0 minus a square root of c. That is why we have used this plot, that is lambda m versus root over of c or square root of concentration, where a is a constant which depends on temperature, then solvent of course water in most of the cases, and electrolyte. Electrolyte means the nature of the electrolyte, whether it is a 1:1 electrolyte or it is a 2:1 or it is a 3:1 and so on, and also electrolyte. Okay. So, therefore, in case of weak electrolyte, you cannot use this linear method of getting this lambda m. So, that is why we need to invoke the concept of this Kohlraasch's law of independent migration of ion, that at infinite dilution all the ions move freely, and therefore, each individual ion contributes to a definite extent to the lambda 0 m value, and that this is the way you can find out. So, let us look at this acetic acid again. So, how to find out this lambda m 0 for CH3 COOH. So, you can find out by means of this expression that lambda m 0 HCl, then plus lambda m 0 CH3 COO minus Na plus, and this minus lambda m 0 sodium chloride. So, these are all strong electrolytes. So, there is no problem in finding out lambda m 0 HCl or lambda m 0 CH3 COO minus Na plus or lambda m 0 NaCl. So, that is why if you make use of these numbers, then you should be able to find out lambda m 0 for acetic acid. The idea is that if you think about, say for example, lambda m 0 HCl, it is nothing but lambda 0 for Cl minus plus lambda 0 for H plus, and few numbers, I mean few values for this lambda 0 are like lambda 0 means infinite I mean this molar conductance at infinite dilution, that is we can write like this, lambda 0 for various ions at infinite dilution, where the unit is Siemens centimeter square mole inverse, where ion is, say for example, H plus, its value is 349.8. Then for example, lithium plus, its value is 38.6. In the same way for other ions, I am writing few of them, that for example, calcium 2 plus, it is 119, calcium 2 plus, or maybe I mean for say for example, CH3 COO minus, its value is 40.9, then OH minus, its value is 199.1, then Cl minus, it is 76.4, and so on. So, therefore, suppose for example, if you want to find out say for example, the lambda 0 m for say HCl, then it will be lambda 0 H plus lambda 0 Cl minus. So, just plug in the respective values for lambda 0, and that will get you the value of lambda 0 m HCl. Okay. Now, the point is how to find out this lambda 0. So, there can be various ways. One is by trial and error method, that you find out this and find out this experimentally. Okay. I mean in order to find out this from experimental data. So, what you have to do, you just consider several different types of combination of this chemicals means electrolyte, and then by trial and error method you plug in different numbers for this positive counterpart and the negative counterpart, and you may be able to find out or you may be able to arrive at some numbers which will a faithful value for these lambda 0 quantities for maybe different ions. But best will be to find out the mobility of ions, and basically lambda plus is expression is F into U plus, or lambda 0 plus is equal to F U plus 0. So, by experimental procedure, there are several methods by which you can experimentally find out this mobility. Mobility is basically the speed per unit potential gradient, that is volt per centimeter, that unit. So, unit potential gradient, how much of distance that the respective ion is moving, that is called the speed of ions and or the ionic mobility. So, this is your Faraday. So, this number 96500 times this will furnish you this lambda 0 plus. So, this way you can find out these numbers, okay, experimentally, and then plugging in these numbers as per requirement, you can find out this lambda m 0 for different electrolytes. So, therefore, for lambda m 0 CH3 COOH, you are applying this Kohlrass's law of independent migration of ions, lambda m 0 CH3 COO minus lambda m 0 NaCl. So, plug in respective numbers and you should be able to find out this lambda 0 for weak electrolyte. So, therefore, direct determination of lambda 0 for weak electrolyte is not possible, because the lambda m versus square root of C, this is not a linear trend. That is why you have to make use of this indirect method of finding out this lambda m 0 for weak acid or weak electrolyte. Okay. So, now so what is the what can be the application of these numbers, this lambda m 0? So, one of the important applications is to find out the degree of dissociation, of weak electrolytes. As I mentioned to you that why this conductance, molar conductance of weak electrolyte follows a nonlinear trend, that is because of this variation of degree of because of degree of dissociation, because with dilution the percentage of the undissociated acid or electrolyte will change, and as a result of which the amount of ions will increase, and as an amount of ion increases, so it adds to the conductance of the medium, and therefore lambda m increases. So, degree of dissociation is alpha, is basically expressed like this: lambda m divided by lambda m 0. So, lambda m 0 means it is assumed to be maximally dissociated, and it is dissociated to some extent at a given concentration. So, it is called the conductance ratio. So, basically for weak electrolytes, say Ha, that gets you A H plus A minus, say it is an acid. So, 1 minus alpha gets you alpha and alpha. So, therefore, if the concentration is C, so it is C. So, therefore, your equilibrium constant is equal to C alpha square divided by 1 minus alpha, and therefore, if you plug in the expression for this, it will get you C lambda m square divided by lambda m 0, and then lambda m 0 minus lambda m. So, that will furnish this Ka, okay, that is acid constant for weak acid. So, basically lambda m means it is not it is at some concentration. So, you will get it experimentally this number, because from the graph, say for example, over here from the graph, if you want to find out say lambda m for say some concentration over here, then the corresponding value is this. For a given concentration value, you are getting lambda m at this point. So, therefore, you plug in this information to the numerator, and the denominator comes from this application of Cole-Russell's law of independent migration of ion. So, therefore, this will furnish your alpha, and you plug in this alpha value over here, it will give you some number over here. So, therefore, it is basically the difference in molar conductance at infinite dilution, and it is the molar conductance at some concentration. Okay. So, this way you can find out the value of Ka for an acid, and similar will apply for weak base or maybe some other weak electrolyte. So, conductance, this is your conductance ratio. So, conductance ratio, by the application of conductance ratio you can find out this quantity. Okay. So, few more points regarding molar conductance. Molar conductance. So, lambda m is equal to kappa divided by C, where kappa is Siemens meter inverse, concentration is mole per meter cube. Now, this C is basically conductance equal to specific conductance into A by L. So, A by L is basically 1 upon C, that is why lambda m is equal to kappa by C. Okay. Now, so basically specific conductance into A by L is your conductance. So, conductance is basically here, this is lambda m, molar conductance. Okay. So, so now next is if kappa is expressed as Siemens centimeter inverse and concentration is expressed as mole per centimeter cube, then lambda m comes out to be Siemens centimeter square mole inverse. Okay. Now, occasionally lambda m is expressed like 1000 kappa by C, where C is the molar concentration, and lambda m is Siemens centimeter square mole inverse. Okay. So, so basically this can be expressed with this expression, but make sure that you adhere to certain restrictions with respect to the usage of concentration unit. Now, at the same time, parallel to the molar conductance, another term is used which is called the equivalent conductance. Equivalent conductance. It is nothing but definition is same, only thing is that it is the, in this case your solution will contain 1 gram equivalent of dissolved electrolyte. In place of 1 mole of electrolyte, your solution will contain 1 gram equivalent of electrolyte, and basically the relation between lambda m and it is lambda equivalent, or simply it is written lambda. Okay. So, relation between lambda equivalence and lambda m is equal to Z into lambda equivalent, where Z is nothing but nu plus Z plus equal to nu minus Z minus, where it is nothing but the charge number for the electrolyte in question. Okay. So, either equivalent conductance or molar conductance one can use for any kind of studies. Now, basically equivalent conductance or molar conductance, why this term is more important compared to specific conductance, because here we compare say two electrolytes having some equivalent conductance or molar conductance value with respect to their conductivity. So, how to compare these two solutions? So, in that case, in order to have a good comparison, you need to have one thing common, that is either the compared solutions will have the same amount of or same mole of dissolved substance, dissolved electrolyte, or same gram equivalent of dissolved electrolyte. For comparison, it is more handy than this simple conductance. So, that is why molar conductance, or in some cases equivalent conductance is used. Okay. So, so that is more or less regarding that is all regarding this conductance or specific conductance business. Now, few simple problems that one can try out, like calculate question, like standard question like calculate lambda m 0 for say calcium chloride or MgSO4 using standard data. So, that means standard data for lambda 0, say for example plus, or lambda 0 minus. So, I have given you some numbers, some data, for some of these ions, but if you consult any standard physical chemistry text or textbook on electrochemistry, you will be getting a bunch of such numbers. So, for that you have to you have to make use of those numbers, but in this case you have to consider one thing, that here the stoichiometric coefficient for this chloride is 2. So, therefore, this stoichiometric coefficient must be taken into consideration while calculating this, because here you have 2 chloride ions against 1 calcium. If it is sodium chloride, then 1 sodium is there with 1 chloride, here 1 calcium is there with 2 chloride ions. So, therefore, so 2 chloride ions means it is double in number. So, contribution from chloride will be double, okay, compared to the contribution from calcium. So, that means whatever lambda plus value is there, you will just consider, and then twice the lambda 0 minus value for the contribution of the anion. Okay. Here it is just 1 by positive and 1 by negative. So, in that case stoichiometric coefficients are basically 1. Okay. So, make use of this standard table or standard data, try to find out, try to calculate this lambda m 0. Next is estimate the value of lambda 0 m for acetic acid, which you are given some numbers. If lambda m 0 for NaCl, say HCl and sodium acetate is given, or in place of this you can use the standard data to find out this lambda m 0 for NaCl, HCl and sodium acetate, and then plug in these information to the appropriate equation to find out this lambda 0 for CH3COOH. In the same way, if the conductivity is given, another question, if conductivity of solution is given, so can you find out the dissociation constant of weak electrolyte? Like I just explain to you. So, finding out or estimation of dissociation constant of weak electrolyte. From conductance data. Another thing is another simple question that why does specific conductance decrease with dilution? Why kappa decreases with dilution, and while lambda increases. This I already have explained to you that kappa is basically related to the number of ions present within unit cube. So, if you dilute, so number of ions within unit cube that is decreased. So, therefore, kappa decreases, but for lambda m, since it is nothing but lambda m is kappa into volume. So, volume increases enormously, although kappa reduces. The effect of increase in volume is so much compared to the decrease of kappa. So, ultimately lambda m suffers an increase, I mean some lambda m increases from certain value to another value. Okay. So, so these are all some simple questions that that you can ask to yourself, and then you can find out the solution to this. Okay. So, next is we'll move on to before we move, another question that just come in my mind, that why AC is used to measure conductance that is for electrolytic conductance of electrolytic solution, electrolyte solution, and why platinized platinum electrodes are used. Okay. So, this is because of the fact that if you use AC current, then if the alternation, that is, this it is a sine or maybe cosine curve. So, if it is symmetrical in each half cycle, then what will happen, that this will produce a pair of oxidized and reduced product at 2 electrodes, and in opposite cycle those two, basically that pair will be produced, but in reverse way. And so, that is why, and if you use a platinized platinum electrode, then those two will be combined like oxygen and hydrogen, okay, and combine to produce this water bag. So, therefore, this electrode is not affected, but in place of AC, if you use DC, then the electrode reaction will take place, and eventually the electrodes will be covered with gas like oxygen and hydrogen. So, the electrode will be affected, and therefore, measurement of conductance will be hampered. Okay. So, now let us move on to another phenomena, that is your generation of electricity, conversion of, in this case basically making use of chemical energy to produce electrical energy. So, basically it is called electrolytic electrochemical cell. Okay. So, here whatever energy is released in a chemical reaction by means of a specific arrangement. Specific arrangement means you dip electrodes and that energy will be captured by the electrodes and it will be converted in the form of electrical energy. So, that is a device in which one can convert chemical energy into electrical energy. Okay. So, think about a simple chemical reaction, that simple chemical reaction that you have two beakers, one is having zinc rod dipped into say zinc sulphate solution. In the other beaker you have copper rod dipped into copper sulphate solution, and then you join these two solutions. Okay. Basically, if you just mix them, then zinc sulphate and copper sulphate will freely mix, and then the situation will rather be more complicated. That is why you keep this separate, this unit separate, and then you join these two by the help of a chemical. It is electrolytic. It is I mean you join by electrolyte. Which is called your salt bridge, which contains some electrolyte, either it is ammonium nitrate or potassium chloride in agar gel. So, that it is full of potassium ion and chloride ion or ammonium ion and nitrate ion in this, and this is basically acting as the joining line. So, it is an electrolytic joining line between these two solutions. One is copper sulphate, another is zinc sulphate, and good thing is that neither zinc sulphate nor copper sulphate is able to mix with each other by this arrangement. And then you have, if you connect with with these two rods, then you will be finding that that current is flowing in this direction. This is minus electrode, this is plus electrode, okay, and plus of the cell, minus of the cell, and your galvanometer is showing a deflection, and electrons are moving in this direction. Okay. So, this is called salt bridge, which contains KCl or NH4 NO3, some electrolyte. So, what is the chemical reaction that is taking place as overall? Zinc solid, that is rod, plus CuSO4, that gets you zinc sulphate plus copper solid. So, that means zinc will be oxidized and copper sulphate will be reduced. Okay. So, basically what you do in a regular laboratory experiment, what you can do? You take some copper sulphate solution and sprinkle some zinc dust. Then you will see a change where the copper sulphate will be replaced by zinc sulphate, and copper solid, red copper solid or reddish copper solid will be produced. So, basically here because of this chemical reaction, some chemical energy is generated, which will be transformed into the electrical energy by means of this arrangement, this device, which is called the electrochemical cell. Okay. So, electrical potential difference is found for this one is about 1.1 volt. Okay. So, for concentration of zinc, because it is very important that this number will depend on the concentration of these ions 1 mole per dm cube decimeter cube. So, it is called a galvanic or voltaic cell. Okay. So, electrolytic cell. So, so this is a device for carrying out in electrolytic cell, that is a device for carrying out this non spontaneous reactions. So, basic principle is like this. In one case you will make use of the forward reaction, I mean and for the back reaction you are making, I mean for the back reaction you are applying some potential from outside, that is, that will reverse the direction of the process. Okay. So, therefore, what is exactly happening? So, this basically this arrangement is called the Daniell cell. Daniell cell. So, think about this part and that part. Okay. So, if you combine these two, then this circuit will be completed and current will flow. So, this part is called, so it is a complete cell. So, if you divide into two, this is called one half cell, this is called the other half cell. Okay. So, half cell reactions, or these are called the reduction oxidation couple. So, here oxidation is taking place, here reduction is taking place. So, this is plus and this is minus of this cell. So, this two together is called redox couple, or it is one half cell, this is another half cell. So, now let us consider the half cell reactions. So, let us try to represent in terms of half cell reactions. So, half cell reactions. Okay. So, reduction process. Reduction process is Cu2 plus twice electron gets you Cu solid 0. So, this is reduction. So, complementary to this reduction process there will be oxidation. So, oxidation process, zinc will give you zinc 2 plus twice electron. So, this is an oxidation process. So, basically what is happening, so the Gibbs energy of the spontaneous redox reaction is converted to electrical energy. So, Gibbs energy basically gives free energy. Gibbs free energy is the free energy that is involved over here. Free energy changes in some free energy change is involved for a spontaneous change. So, for a spontaneous process delta G is negative, that is change in Gibbs free energy is negative. So, if it is a spontaneous reaction, then the spontaneous reaction, for the spontaneous reaction, this type of half cell arrangement, when these two are combined one with another, then this Gibbs free energy for the spontaneous redox reaction will be converted to electrical energy, and this change in Gibbs free energy, if that is delta G, that is nothing but NFE, where E is the cell potential, F is Faraday, N is the number of electrons transferred. Okay. Like here 2 electrons are involved for the reduction of copper, and also 2 electrons are liberated. Here 2 electrons are used up and 2 electrons are liberated. Okay. So, this liberation and this used up using. So, these two usage and liberation, these are equivalent. So, this is compensated by this one. So, therefore, the reaction will be complete. So, N is 2 for this particular case. So, delta G is equal to NFE. So, if delta G is negative, then you expect to have E to be positive. That means, you will have some positive cell potential. Okay, so this galvanic cell is an arrangement where you can catch this free energy change and then you convert this into electrical energy, so that this electrical energy can be used for doing some work, some useful work. It is not like a pressure volume work. It is this electrical energy can be used up to do some non PV work, some effective work. Okay. So, in galvanic cell what is happening, that if you recall the last earlier slide, that here you see that in zinc sulphate solution your zinc metal is dipped, or in copper sulphate solution your copper metal is dipped. Okay. So, therefore, whenever such an arrangement is happening, is made, then it is represented like this. So, for galvanic cell you have metal and you have electrolytic or electrolyte solution, and a vertical line to just indicate that this is nothing but the interface of the metal and electrolyte. Okay. So, basically electron transfer means the electron transfer from metal to electrolyte or electrolyte to metal happens at this interface. So, a single vertical line is just to represent that this metal is dipped in this electrolyte solution, like copper is dipped in copper sulphate solution. Okay. Now, if there are two electrolytes like here, you see one is zinc sulphate, another is copper sulphate, then these are connected with the help of a salt bridge. So, how to represent this arrangement? So, this arrangement can be represented like this. So, electrolyte 1, then electrolyte 2, and they are not physically mixed. I mean you are not mixing copper sulphate with zinc sulphate. So, they are kept in separate containers. So, but they are connected with the help of a salt bridge. So, this arrangement is represented by writing these two electrolytes side by side and putting two vertical lines in between. So, that represents the salt bridge. Okay. So, that bridges this electrolyte 1 with electrolyte 2. Okay. So, whenever this arrangement is made, that means you have this half cell, you have this half cell. So, total potential is nothing but the potential difference between these two. So, therefore, this half cell should have some potential, this half cell will also have some potential. Whether it is this electrode is positively charged with respect to the solution or it is negatively charged with respect to solution, that decides whether in which direction the electrons will be flowing. If this is electron rich, suppose if this is electron rich or if this is electron rich, then what is happening, that electrons will be accumulating over here, and if this is electron deficient, then this solution will be having more electrons. So, therefore, what will happen, therefore, as a result of which this is deficient, this copper rod is deficient. So, therefore, electrons will be flowing in this direction. So, and through salt bridge the circuit will be completed. So, why this one is electron rich? This is because of the fact that the moment you dip zinc in zinc sulphate, so it will lose 2 electron, and the zinc will have the tendency to go to the solution as a zinc 2 plus. So, these 2 electrons, the zinc atom will leave over here. Okay. And here what is happening, this copper sulphate will accept 2 electrons, okay, 2 electrons from here, okay, and will become copper 0 and will be deposited over here. Okay. So, therefore, this will be deficient in electrons. So, as a result of which this one will be positively charged and this one will be negatively charged, and therefore, this is, I mean, this electron will be flowing from this from here to here. So basically it depends, I mean whether the forward reaction or the backward reaction will take place. I mean when you dip one metal in a solution, like say for example, if you dip a metal in a solution of its constituent ion, that means this half cell will be reversible with respect to that particular, and say for example, if it is zinc and if it is zinc sulphate, then it is said that the electrode is reversible with respect to sulphate. So, it is zinc, then zinc 2 plus twice electron. Okay. So, the thing is that, so whether zinc will try to be oxidized or copper will try to be reduced, that depends on the specific characteristic of the metal in question. Okay. So, that is what is called the half cell potential. So, if half cell potential half cell potential will dictate whether zinc will have higher tendency to get oxidized or copper will have more tendency to be oxidized. Okay. So, therefore, whenever we talk about this redox process, then basically you can represent this electrode reaction like this, or you can represent electrode reaction zinc 2 plus twice electron gets you zinc. So, this is called the oxidation scheme, this is called the reduction scheme. So, the corresponding potential what you express, it is called the oxidation potential, and this is called the reduction potential. So, actually oxidation and reduction potential, they are related to each other by a negative sign. Okay. If oxidation potential is x, then reduction potential will be minus x. So, therefore, zinc 2 plus twice electron or zinc 2 plus twice electron getting you zinc. So, we have to follow a specific convention, which is the UPEC convention, that we should use the reduction scheme always. Okay. Although oxidation scheme can be used, but reduction scheme is prescribed by UPEC. So, therefore, zinc 2 plus twice electron zinc, and corresponding phi means the potential that is developed at this electrode with respect to this solution is called the electrode potential. Okay. So, therefore, phi say for example, zinc 2 plus zinc, it is represented like this. So, the corresponding potential, reduction potential will have a representation like this. In the same way, copper 2 plus twice electron gets you copper 0, and therefore, phi Cu2 plus Cu. So, therefore, in order to express the cell potential, what you have to do, that E cell will be equal to, is given like this, phi right minus phi left. What is phi right? Phi right means that is you have one cell, I mean like this. Okay. So, place the electrode where this reduction is happening. Okay. So, like here you have reduction means copper over here, and oxidation is zinc over here. So, therefore, whatever phi in reduction potential scheme, it is phi right, okay, and this is phi left, it is in again in reduction scheme, but it is phi left. So, your cell will be phi right minus phi left, because you need to have E cell which is greater than 0 to make the whole or the overall cell reaction spontaneous. Okay. So, therefore, in reduction in right hand and oxidation in the left hand, but where phi is nothing but the reduction potential. Okay. So what do we get out of it? So, therefore, it is in reduction scheme, Okay, reduction scheme means reduction potential scheme, that is using reduction potential convention as prescribed by UPAC. So, E cell is equal to phi right minus phi left. Now, there is still another term used for this reduction potential, is called the standard reduction potential. Okay, standard reduction potential. So, standard reduction potential is the or the standard half cell potential is expressed as phi 0. It is nothing but the potential or the half cell potential when the electrolyte concentration is 1 or unity, concentration is unity for concentration, or when the activity is unity, activity of say for example, zinc sulphate is unity. Okay. So, the corresponding potential or half cell potential will be called as the standard half cell potential. Okay. So, therefore, what we get, that E cell is the cell potential is nothing but phi right minus phi left in reduction potential formulation. Now, next is how to measure the cell potential, that is the electromotive force, or the what we measure, like in case of a cell, it is written that 1.5 volt. Okay. So, how to measure that? Okay. So, to measure that, you may use a standard voltmeter, but this standard voltmeter is not recommended because of the fact that if you use a voltmeter, that draws a lot of current. So, if it draws a lot of current, then reversibility of the process, because whatever we are discussing, it is based on the condition that the reactions are reversible. Okay. So, in order to maintain the reversibility of the process, you need to draw minimum current. So, therefore, EMF is nothing but EMF, or electromotive force, is nothing but the cell potential. So, EMF is nothing but cell potential when limit this current goes to 0. So, that means you measure the cell potential with a device which does not draw too much of current. So, that is called the EMF, or electromotive force. Okay. So, therefore, what are the things that we have used over here? One is half cell. Okay. Then when it is half cell, then half cell potential like phi, then reduction potential scheme, where you have to represent the reaction in reduction scheme, like copper 2 plus to copper, zinc 2 plus to zinc. So, that is why these phi's are used here, are reduction potential. Then another thing we have come across is the standard reduction potential, when the concentration of the active ingredient is, or the ion is unity, or the activity of the constituent ion is unity. Okay. That is ion with respect to which it is reversible, like for example, this is reversible with respect to copper 2 plus, this one is reversible with respect to zinc 2 plus. Okay. So, when we have got this half cell potential, then it is customary to connect this to half cells to form your cell. So, when we have formed this complete cell, then the question of E cell comes. So, therefore, how to calculate or how to estimate E cell? It is nothing but phi right minus phi left in reduction scheme. So, therefore, next comes one thing, that how to find out this E cell. You can use a voltmeter, but voltmeter is not a good job. So, you use that is called the galvanometer, and with the help of a specific method which is called the Poggendorff's compensation method. Poggendorff compensation method. With the help of this method, you compare the no deflection point for your unknown cell and for a standard cell, and then you just take the ratio, and you will be able to find out that when I mean the ratio of these two quantities, and as a result of which, in that case, in that particular arrangement, the current goes to 0, and you will be able to find out the EMF, which is called the reversible cell potential. Okay. So, this is the method by which we can find out the cell potential. Cell means it is a combination of two half cells. Okay. So, that is about this the preliminary of this galvanic cell. So, in the next lecture we will take up several other examples of such cell, such galvanic cell. We will consider many reactions, and also we will try to construct various cells based on certain chemical reactions, and we will take up some simple examples of this electromotive force or EMF measurement. Electromotive force means reversible, that connects the reversible electrode potential. Okay. So, and also we will try to have an attempt to find out the half cell potential. Half cell potential means what is the potential for a specific half cell. So, in that case you have to make use of a known half cell, and then with respect to that known half cell you construct the complete cell, and then find out the EMF of this complete cell, where one half cell is known and the other half cell is unknown. Okay. So, this way we should be able to find out the half cell potential. So, we will take up the measurement of half cell potential in the next class, and various applications of EMF measurement, some of the applications of EMF measurements in the next class. So, that is all for today. Thank you.